So hello everyone, this is a presentation about the beyond 5G technologies that are going to be used in the context of the UWS testbed in the 6G-PATH project. My name is Jose Alcaraz from University West of Scotland. So the purpose for this meeting is the agenda is divided in three different steps. The first one is I'm going to be introducing a background ground floor in order to explain a little bit these pre-6G architectures. And later on, I'm going to be focusing in two key technologies that are the beyond 5G technologies that has been created in the context of other European projects and that has the potential to be exposed, integrated into the facilities on the testbed of the 6G-PATH. So let me start a little bit explaining this multi-tenant beyond 5G or pre-6G architecture, okay? So what you see here in the screen is mobile phones, UEs, connected to a radio access network, connected to distributed units. And then here you have the edge of the cloud with several instances of the edge. And in the edge, we have a virtualized infrastructure with multiple digital service providers or tenants and the physical or the infrastructure service provider. Then we have the transport network, and then here we have the core network. Here we have later on the multi-domain segment, okay? So then this is in terms of the data plane. In terms of the management plane, we have a separated network layer here to do the management of all these compute and workings, etc. And we also have a service layer, which is no more than a place where we have mirroring capabilities of the switches. So we do some processing offline, not inline in the data plane. This is really speaking a hello world on these testbed facilities. Worth to mention that in this kind of pre-6G architectures, the first challenge associated is that the traffic of the end-to-end traffic, it's polymorphic. It's changing the shape along the different steps involved into the data path. For example, at this particular point in the network, we have GTP encapsulation. At this particular, to allow user mobility, or at this particular one, we have VXLAN encapsulation to allow tenant isolation, traffic of tenant isolation. For example, so this makes challenges to be addressed. The second challenge is that it's a multi-stakeholder architecture. So we have different instantiations of services running into the same physical hardware. So in this particular case, we are seeing here two different mobile network operators. One is the DSP1, composed by edge and core, and the other one is the DSP2 here. But have in mind that here, I put here a UBF, but in reality, this is the complete pre-6G architecture, okay? So we put it there for simplicity. Now, keeping this in mind, another of the challenges associated is that there is a significant mismatch between the virtual and the physical security perimeter, okay? So because the one is the virtual perimeter associated to each of the tenant, the other one is the physical perimeter associated to the ISP. Later on, we have super high-speed network, which is putting a lot of pressure into the management and the control layer, and very dense network. So we are talking here of 1 million of devices connected here. So now, this is the background. Now let me open up a little bit more of the background. This is the last slide on this, on management plane. So now what I'm going to be doing is zooming this particular management layer here, okay? So usually in this kind of management planes, we have sensor agents that allows us to get together the status of the resources, of the services, and also on the network flows, on the communications. We have the aggregation and prediction layer, which in summary allows us to aggregate metrics. These are raw metrics, these are aggregated metrics, are also predicting metrics. Metrics that are based on the future, on 2 seconds ahead or 1 minute ahead and so on. So then the analytic layer will take into account all the information related to these metrics, etc., and will provide alerts. Decision making will take alerts based on predefined behaviors on the system, will perform decisions. Then the planning layer will take the decisions and perform a very concrete implementable plan that later on will be orchestrated by the orchestrator performing a set of ordered actions that are later on enforced in the actuators that are controlling the infrastructure. So this is the different functionalities available into the management plane. And finally, we have a closed autonomous loop that is providing a pipeline between all these components, performing every of the different steps from sensing to actuation in order to perform automatic or autonomic management of the network. Each of these sensors or components, let's say, can be governed by rules or can be governed by AI models. Okay, each of these approaches has advantages and disadvantages. And now, to finalize the architecture, we have also inventory agents with the main purpose to share the topology of all the whole infrastructure to all these components so that they are topology aware. Okay, this is the summary of the concept, and this is the basic classic autonomous control. Now, let me start now explaining what are the challenges related to this classic approach. The first one is we have back propagation on cascade. Let me explain. If we have a bug in this component, this is going to be affecting the whole loop. I mean, and the sooner the bug is detected in the loop, the more cascading effect you are having in the rest of components. Okay, this is the first important aspect here. The second one is that it requires production-ready components. I mean, they cannot be kind of prototypes on low TRLs, because when you push, the loop needs to be closing very quick, very efficiently, scalability, and so on. This puts a lot of pressure in development and research. Okay. Also, it requires very complex sensing and actuation layer and infrastructure. This part below is incredibly complex because we are now dealing with 6G, with a lot of control plane, with a multi-tenancy, isolation, Kubernetes, OpenStack, and a lot of different technologies that need to be compatible with these sensors, actuators, and inventory. Also, the rules, if we go for the rule approach, are error prone. I mean, you put rules, you check the behavior, but the rule could be a problem, right? So we need to refine them. The AI is based on data-driven, so we really need first the data set in order to allow the AI to learn, in order to produce these controls, okay? One of the main problems associated to this kind of architectures is that it's a slow response, because you need to pass by every component, even if they are not providing any added value. So then in our proposal, in our different projects, what we have is what we call shortcut closed loop architecture. In summary, the components are exactly the same, but the loop can be created ad hoc based on the use case. The only requirement, so any possible loop of interaction between components is possible. It's use case dependent. And the only limitation here is with respect to the sense of the loop. I mean, it always needs to flow in that direction, okay? For example, what you see here is a loop where the sensor agent itself is providing a decision directly, and the planner is providing the actuation into the network. That is the ground of the technologies I'm going to be presenting, okay? Now, the first technology is coming from the 6G Brains project, and in this particular technology, what we have is a set of inventory agents that allows us to discover the topology of the pre-6G architecture in order to populate the whole understanding of the topology. Later on, we have a graphical interface. This is human planning, it's not automated, which decided where to do the enforcing on the slice based on the topology. And finally, the slicing is going to be sending that places to the actuators that will perform the enforcing of the slice. Just for everyone to understand, slicing is the capability to provide an isolated logical network over the same physical network with performance isolation. I mean, if the slice is isolated, no other traffic will interfere into the capabilities associated to that particular slice. Now, let me explain a little bit. Here we have three components involved: topology, inventory agent, actuation agent, and slicing graphical interface. Let me explain a little bit this topology agent. So this is based on an open source Skydive software. So everything is based on open source. This Skydive is a project coming from IBM originally, which what we have been doing is creating algorithms to perform the automatic discovery of topologies using the Linux kernel inventories, the Cisco Discovery Protocol and LLDP and SNMP to walk across the different devices in the network. We also have been using proofs to integrate with OpenStack and KVM for virtual computing, also with the Linux namespaces, Docker, LXCs for containers, with OpenVSwitch and Linux bridges for virtual networking, and with OpenAI FlexRig and the Nokia UDR for the control plane of the pre-6G or beyond 5G architecture. With all this, that allows us what I'm going to be showing later on in a video, okay? But let me, before we go to the video with this more the graphical interface, let me explain what our control in the network is able to do, okay? So we have a RAM-based slicing, which is again based in open source project. We are using OpenAir interface, FlexRAN and FlexRig, and also the Nokia UDR interface. And in terms of core slicing, we are using different open source softwares like the Linux traffic control or OpenVSwitch, and also the Net FPGA, which is a programmable FPGA card. But also we are relying on the most advanced network cards available in the market. For example, the Mellanox Connect 6 or the Netronome cards, etc. I mean, the main purpose of this control is to expose, or has been extended, because all of them are existing. They have been extended to support network slicing and to provide a unified intent-based interface so that we can interact with all the technologies under the same API. Now, if we join both together, the result is what you see here. This is one of the testbeds that we are using right now in the context of the 6G-PATH project, okay? We have the other one in the data center. We have two small testbed and a big one. This is our pre-production, let's call it. And what you see here is we have here the RAM, okay? The radio access network. This RAM is later on being connected to the edge. We have two different edge segments here. And the edge later on is connected by the transport network located here. We have four different networks here. And then after this, we go to the core network over here, different components on the core network. We have as well the management network here. This is the in this particular use case is the final end use. Okay, we have mobile phones and the final end use, the final destination of the traffic. In this particular one, we are sending video and EtherCAT industrial traffic through this network, and we have here the management interface. And what we are going to be doing is the traffic is going to be passing from the mobile phone to the edge, to the segment, to the core, etc., arriving to the final destination. Okay, so now in this mind, what is the technology about? So what you will see right now is how we are going to be intentionally inserting a congestion problem in the network, so the video will be degraded, okay? And also the EtherCAT traffic will be also affected, okay? This is the result of this congestion. I mean, we are applying artificially some congestion in the network. And of course, the video is losing packages and the EtherCAT traffic is being affected. Now, what we are going to be doing is using this end-to-end network slicing in order to restore the quality of those critical services. So what you see here is, roughly speaking, we are now, what you are going to be seeing right now in the screen, this particular screen, is the automatic discovery of the whole topology of the data center. So this is and later on, after we discover the topology, we are going to be selecting the end-to-end calculation of the network slicing, and we are going to be applying different control actions over the whole data path, okay? So this allows us to control compute and network, okay, in this particular interface. So let me explain a little bit now the topology. So what you see here, and let me see if I can stop the video up to here. So what you see here is exactly the same two edges that I explained before in the video and the core. So what you see inside are all the virtual switches, the virtual machines, the Dockers, the switches, interconnection, routing available inside of the box, of the physical box. For example, these particular three components here are the switches, the physical switches that interconnect the computers. And this one here is the UE connected to the radio access network and the DU that is connected to this particular edge, okay, in this case. So now what we are going to be is selecting an end-to-end, for example, from the UE to the last part of the UPF, okay? In this particular scenario, we are using the open air interface UPF. Okay, we select the start of the path, let's say, and we are going to be selecting the end of the path, and we are going to be automatically calculating every single endpoint and devices across the virtual and physical interfaces that are creating the end-to-end. And later on, we are going to be enforcing our slicing in every of the single points that has been calculated. Okay, so as a result of this slide, we created in this demo 2 different slices. One for the video traffic to be restored, and the other one to preserve the Ethernet traffic, the EtherCAT traffic. So the congestion still happens. However, the video has been preserved at top quality, and the EtherCAT is still preserved at top quality. Okay, that's the summary of this technology. So this technology is already created by design into the same testbed of the 6G-PATH. So we are planning to expose the technology, maybe not to the final end user, but at least to the administrator to run the test into the context of the project. Now, the second technology is related to 2 different projects. I mean, because you remember in the previous technology, there was no real loop. I mean, the loop is manually done by a human here in the planning. In this particular one, we are exercising a small, very preliminary closed loop that allows us to detect attacks in the network, okay, for example, a DDoS attack. And then this attack will raise a decision to the planner, and the planner now automatically, not based on a graphical interface, will decide to enforce the mitigation of that attack, okay, taking into account the topology. I'm not going to explain again these 2 components because they are more or less the same as previously explained, but I put here 2 different projects, the ARCADIAN-IoT project and the RIGOUROUS project, okay? The main difference is the use cases and the evolution and the state of the technology, but the architecture is similar. Let me explain this sensor agent, okay? So we are based in open source tool Snort. Snort is an IDS that allows us to detect, let's say, attacks happening in the network. And what we have been doing is extending this Snort in order to provide the dynamic encapsulation payload support. Remember the challenge I mentioned about the polymorphic traffic in this kind of network? So we have been extending this to provide this support into Snort. And now, what we have is, this is the same architecture. Imagine that we are running here. We have deployed the sensor agent, the IDS, into outside of the data plane, and we only receive a mirror traffic. We did that because this sensor, the IDS, is a little bit putting some delays into the data path, and we don't want in a super ultra fast 6G network where we need 1 millisecond delay to put a lot of milliseconds in processing in the middle. So this is what we do, offload processing. Then we put here the planning, and then we have a distributed actuation agents distributed along the different let's say, elements or computes in the network. Then what we do is we run a normal traffic. This is the traffic, the background traffic of the architecture. And very soon we intentionally set up a cyber attack. Then this cyber attack is being mirrored, of course, everything is mirrored to the sensing agent. And as soon as we start a cyber attack, the sensing agent will produce an alert. The planning will determine what is the best place to perform the attack, the mitigation. In this particular project, in the ARCADIAN project, what we do is we drop, it's a firewalling, we drop the attack in the closest place to the source of the attack. So in that particular case, it's decided that in this particular network interface here is the most effective place to stop that particular malicious flows, okay? So this is, again, it's a small loop that allows us to do the firewalling capabilities. Then this is the ARCADIAN-IoT. We extended this later on. RIGOUROUS is a continuation in our developments in the ARCADIAN project, where we, in that particular case, we do exactly the same. I mean, now we launch the attack again. The sensor will perform the type of alert. The story here is now the planning will determine that not a firewalling capability, but will perform an end-to-end slicing, which is similar or not similar, but the same idea or capabilities that we expose in the 6G Brains project. So in this particular one, we do a distributed mitigation where in all the different places in the network, we are performing that setting up of a network slice. And then as a result, the traffic is not blocked, but is very, very thin. It's a very disadvantaged traffic, maybe 1 kilobit per second or so, okay? So I guess that you can understand that the potential for the 6G-PATH in order to isolate different network conditions or pre-6G network conditions for the use cases that we need to run into the test. Okay. Now, this is a video that this is a very recent video, it's less than 3-4 months, where we expose this use case live. Okay, so I'm not gonna, because this explanation here is more or less the same explanation that I have been already mentioning. Okay, it's a combination or a joint effort between Orange, Romania, University of Murcia, and University of West of Scotland. This is our interface. So let me explain what you have here. Okay, in this interface, you have the traffic going to the edge on these two, let's say, graphs. It's on real time. Okay, this is a real time interface. In this one, we have the traffic going through the transport network, and in this one, we have the traffic going to the core. Okay, but the core is the closest to the victim, and the edge is the closest to the attack. Okay, this is intentional. Okay, because inside of the edge we have plenty of different interfaces, and the same happen in the core. So we decided the closest ones. Okay, and now what you see in the top part in green is the legitimate traffic. Okay, in this particular case, I can't remember the background service, but what I can tell you is that it is a TCP service. Okay, I believe it's a multimedia TCP service. But this is why you see here two different graphs. You have the normal TCP connection, and you have the acknowledge, which also consumes some bandwidth. Okay, the ACK. In the bottom part, you will see here the attack. So at that particular moment in time, then background traffic is already happening. Okay. It's now here. At that particular time, the first thing we do is that the traffic, hold on, here, the background traffic is happening, and very soon we activate the attack here. You see, so at this particular moment, the attack is being initiated. Okay, so in this particular moment, the whole small loop or shortcut loop that I mentioned before is already taking action. Now the detection is happening. Okay, so later on, the detection is passing to the planning, and the orchestrator, this is what you see here, is now the outcome of the orchestrator already producing some, let's say, concrete actuations into the data plane. And then the actuators receive the information and perform the mitigation in the slice. And this particular, when the mitigation is happening, you will see how only the attacker is now completely mitigated. Okay, but again, now in this particular moment, there is no more traffic into the transport and the core, also in the edge, but we decided to monitor in this particular point to tell you that the attack is still happening. I mean, there is nothing here. So the attack is still happening, but has been fully and successfully mitigated. I believe that this gives you the two main technologies that we have around that are going to be later on exposed or not completely, but a subset can be somehow integrated or reused in the context of the testbed of the 6G-PATH.